All right, welcome to Unit 1.3, Foundations of Chemistry. In this part 2, in this video, we are continuing to talk about key question 2. How do we quantify matter and analyze matter? In this video, you are going to be sure to annotate, and just so you know, there is an optional dimensional analysis video that's linked here and copied onto the assignment. So in the previous video, we talked about chemical and physical changes, and we looked at the different types of chemical reactions. And so now we're going to move into the measurements that we take either before, after, or during those chemical and physical changes. Starting with mass. Mass, we can use something like electronic balance to measure, and it measures the amount of a substance, so the amount of a substance. And the units typically are grams, kilograms, and we don't use pounds, but pounds are a measure of mass. We don't necessarily use that in science because we use the metric system. The next type is temperature. It measures the movement of particles, so fast-moving particles will have a high temperature and slow-moving particles will have a low temperature. Common units are degrees Celsius. Degrees Fahrenheit, again, it's not metric, so we don't necessarily, or it's not standard, so we don't necessarily use it in science, but we do use it in our everyday lives, at least in the US, in terms of weather. And the other one is capital K Kelvin, which is what we commonly use, especially when we're dealing with like gases. Moving on now to pressure, we can measure pressure, which is the force exerted on a substance by a substance on a wall of a container. We can use something like a barometer or whatever to measure the pressure. And common units for that are atmospheres, pascals, kilopascals, torr, and millimeters mercury. The last measurement we're going to look at is volume, which measures the space occupied by a substance, and the units commonly for that are milliliters, liters, and you want to add this onto your notes, centimeter cube, which is actually equivalent to a milliliter. All right, so it's all great that we can take these different types of measurements, but one thing that's difficult for us to do is sort of count the number of particles in a substance because particles are so small. And so what we do instead is we oftentimes use a mole, and we know that a mole is represented by, is equal to 6.02 times 10 to the 23 things, or 602 hexillion things. And we use the analogy that often 1 dozen is 12 things. Well, a mole is like that, it's 602 hexillion things. But as I said, we can't, because we can't count the number of particles so easily, we use a mole to help us do that. It sort of groups the number of particles into amounts that we can more easily measure, visualize, etc. So at the center of all measurements, since we're oftentimes needing to do this, it is the concept of a mole, because if we wanted to convert from one measurement to another, we'd have to go through moles, since that represents the number of particles in that substance. So we can use this mole map whenever we are trying to convert from one thing to another. And I'm just going to give you a couple of examples, and then we'll go through on more in more detail. So let's say I start off with knowing the pressure of a gas, and I want to know from the pressure of the gas, well, actually, how much does that gas weigh? Well, I can simply travel along this road between this red island here with pressure, volume, and temperature. I can travel along this road to moles, and then from moles to mass. So I sort of like map out a route, starting here with where my pressure is, go to moles, and then to mass. No matter where you start and where you end, you're always going to have to go through moles. Let's do one more example. Let's say I'm starting off with mass, and I want to figure out how many particles, like I'm saying I'm starting off with 10 grams of helium. I want to figure out how many helium atoms would be in 10 grams. So again, I start off with my mass. I have to travel to moles first, and then from moles, I can get the number of particles. So these, we can call them sort of like routes. So what goes along these routes? These are going to be the equations that relate moles to these other values or quantities. So let's begin with mass. We can use this equation, moles is equal to mass over molar mass. So you'll notice that this equation has both moles and mass in it, and so that's why it's used along this route. Technically, you can also use this equation to figure out molar mass as well, since that's another variable in that equation. Now we're going to look at moles and number of particles. For this, we use the equation that 1 mole is equal to 602 hexillion things. If we want to go from to and from molarity or volume of a solution, we use this equation that molarity is equal to the moles, it's technically of the solute, divided by liters of solution. And this will be particularly useful for the next unit. The last one we're going to look at is the one for gases, and this is called the ideal gas law. PV equals nRT, where P equals pressure, V equals volume, N represents moles, so N is moles, R is a constant, it's called the ideal gas constant, and when your pressure is in atmosphere and your volume is in liters, the constant is equal to 0.0821 liters. That should be atmospheres, Kelvin, mole. And T represents temperature, and that's in Kelvin. Okay, so let's look at an example of a mole map problem. In this problem, it states how many water molecules are there in 7 grams of water. All right, so we're going to use this Analyze, Plan, Solve, or APS system. Let's begin with analyzing. First, we need to do is identify our givens and what we're trying to find. So we're given the mass of water equal to 7 grams, and we're trying to find the number of water molecules. Notice how I put mass equals 7 grams. It's helpful to actually write out what the measurement or the quantity is representing, because that'll help you keep track where you're at in the mole map. And we're trying to find the number of water molecules. Again, writing that out is super helpful. The next step is to plan. We're going to plan by sort of mapping out what we're going to do. So I have my handy dandy mole map here. I'm starting with mass, so I'm over here on mass. And from there, I want to go to number of particles. So I'm going to travel along this route to moles, and then from moles to number of particles. So my plan is going to be from mass to moles and moles to number of particles. And that's written here. The last thing we're going to do is we're going to solve, and there are actually 2 ways to solve: plug and chug and dimensional analysis. Let's start by looking at the plug and chug method, because I think that's more conceptual. So again, the question was how many water molecules are there in 7 grams of water, and our plan was to go from mass to moles to number of particles. And we're going to use these 2 equations because those were the equations along the routes going from mass to moles and moles to particles. So for the plug and chug method, I'm going to just plug the numbers into each equation one at a time, starting off with the one that relates moles to mass. So I'm going from mass to moles, so this will be my unknown for this first step. So moles is equal to 7 grams over the molar mass of water, which is 18 grams per mole. And I get this number 0.39. So I go ahead and I solve for my moles. Great. Now I'm here, I have my moles, and my next thing I want to do is I want to go to my number of particles. So for that, I'm going to use the equation 1 mole is equal to 6.02 times 10 to the 23 things. Now, there are many different ways of solving it, so here I'm just presenting one that looks the most simplistic, but I know that if 1 mole contains 6.02 times 10 to the 23 things, well, then if I multiply this number 1 by the number of moles that I solved for, 0.39, that'll tell me, that will change this number of 1 into 0.39. And if I do the same thing on the other side, it will give me the equivalent number of particles for 0.39 moles. So that's just the math that I did down here. I sort of just did a scaling method. Anyway, when I did that work and I multiplied both sides by 0.39, I found that 0.39 moles is equal to, contains 2.3 times 10 to the 23 things, or water molecules in this case. And so that's how I was able to get my answer. So just to recap, this plug and chug method is essentially you're plugging in your values into each equation one at a time according to the plan that you mapped out. Now let's look at dimensional analysis. If you were in my class last year, we didn't use dimensional analysis. A few people learned it on their own through video. So this may be new for some of y'all. If that's the case, then after seeing me go through this one problem, I would suggest you watch the optional video. All right. So, in this case, with dimensional analysis is it's not as conceptual, but it is super helpful in terms of there's very little thinking that you have to do because what you do for dimensional analysis, instead of focusing on the concepts, you really just focus on the units, and you utilize your understanding of algebra, particularly what happens when you multiply fractions to get rid of units that you don't want. So in this example, again, we're starting off with 7 grams of water, and we want to get rid of the mass. We want to go from mass all the way to particles, and we're doing that from mass to moles to particles. So the first thing is the units for mass are grams, and I want to get rid of that unit. And I want to keep the units of moles. So to do that, I'm going to have to multiply this fraction by another fraction known as a conversion factor. And that conversion factor will allow me to cancel out my grams and keep my moles. So let's go to the conversion factor. Here's my conversion factor. Where did I get it from? I got it from the molar mass because according to the molar mass of water, 1 mole of water is equal to 18 grams. So essentially I took that information and turned it into a fraction. Now, what goes on top or the bottom depends on what I'm trying to cancel out and what I want to keep. Since I'm multiplying fractions, if I want to cancel out units, they need to be on opposite sides. I'll say that again. Units I want to cancel out should be on opposite sides. So since my grams were in the numerator here, since I was starting off with that, then the second fraction needs to be in the denominator so that they can cancel out. In the numerator, I want to keep moles, so that should be there. So what I do is I took the 1 mole is equal to 18.0 grams, which I got from the molar mass, since that is the definition of a molar mass of water. And I use that to make my first fraction. So right now, if I were to stop and I solve this all out, I would have moles. But that's not where I want to end. I want to go now from moles to particles. So I'm going to do my second conversion factor, and this one is going to come from this equation. 1 mole is equal to 6.02 times 10 to the 23 things. In this case, I want to now get rid of moles, and I want to keep the number of particles or things. So I put moles in the bottom because they need to be opposite. They need to be opposite to cancel out. And because we're multiplying fractions. Okay, so let's just see here how the units cancel. First, we're going to cancel out our grams. Since they're opposites, they'll cancel out. And now we're going to cancel out our moles. Since they're opposite, they'll cancel out. And this will leave us with some math to do. So we can multiply 7 by 6.02 times 10 to the 23 and divide everything by 18. And then that will give us the number of water molecules. So we should get the same answer as we did before, no matter what method we use. All right. If you need more help with dimensional analysis, you can watch this video to give you some other clues on how to use dimensional analysis. When you are ready, we're going to move on to our CFU. All right, so here's the CFU. For each of the following questions, you're going to use the mole map to plan out your solution. So your plan should look like what you saw before, where it was like mass to moles to particles. So you're just mapping it out or planning it out. Then you can choose one of these problems to solve. So that means that you only need to solve one, but you need to plan for all 4 of these examples. When you are ready to check your answer, press play. Okay, so here are the answers for CFU 3. So you can check your answers. If you have any questions, again, you can come see me about questions either during class, after class, or during office hours. All right, hope you found this video helpful. Have a quality day.